Hi everybody, welcome back to our last set of notes for Unit 5A. In Notes 5A.3, we are going to talk about the introduction to finding inverses, function operations, and composition of functions. Let's review some inverse function concepts. First of all, when you see the notation f to the negative 1 of x, that means find the inverse of f of x. For the inverse to be a function, the x's cannot repeat, and it has to pass the vertical line test. For a function to be considered a one-to-one function, the original function must be a function, and the inverse must be a function. When we look at domain and range, the domain of the original becomes the range of the inverse. The range of the original becomes the domain of the inverse. To find an inverse algebraically, you will switch the x and y and resolve for y. To find the inverse graphically, all you have to do is switch the x and y coordinates. Now, if you'll remember, how do we test if f of x and g of x are inverses? Well, f of g of x has to equal x, and g of f of x also has to equal x. Example 1. They want us to find the inverse of f of x equals x squared plus 3. They want us to graph both functions and give the domain and range of both functions. So before I do anything with the inverse, I need to change that f of x to be a y. So I now have y equals x squared plus 3. So the first step to finding the inverse is you switch x and y. So that becomes x equals y squared plus 3. Now I go through the process of resolving for y. So I'm going to subtract 3 from both sides, and then I'm going to take the square root because I have to undo the square. So now because I put the square root on there, my answer has to include plus or minus. So that becomes y equals plus or minus the square root of x minus 3. Now, in terms of graphing, where do we start? Well, the first thing you want to do is you want to come up with the graph of the original function. So my original function is a quadratic, so I'm going to start with the quadratic parent function. And then there is no change from old x's to new x's because the h value is 0. So there is no change on the x's. However, the y's, to go from old y's to new y's, I'm going to add 3. I'm going to add 3 to the y values. So I end up with this table. So this table will allow me to graph y equals x squared plus 3. Now, to find the points to graph the inverse, all you have to do is switch the x and y coordinates. So you don't need to go to the square root parent function and shift off of that. No. All you have to do is take the original function, flip the x's and y's, and now you have the graph of the inverse. So you take the original, switch the x's and y's, and now you have the table for the inverse. Now let's graph both the original and our inverse function. So looking at the original function, the parabola, the x squared plus 3, let's talk about the domain, the range, and then answer the question, is it a function? The domain of the original function is a parabola, so it's negative infinity to positive infinity. The range is k to infinity. In this case, k is 3, so the range is 3 to infinity. Is it a function? Yes. Now let's talk about the inverse. Now, if you recall, when you're doing domain and range of the inverse, you just flip-flop the domain and range of the original function. So the domain of the inverse is the range of the original. So that means that my domain is 3 to infinity. And if you look at your graph, you see that that holds true. Now, the range is the domain of the original. So the range is negative infinity to infinity, and that also fits with my graph. Is it a function? No, because it fails the vertical line test. Now, if you look at the graph, I went ahead and also put the line y equals x up there, and that's just to remind you that to form the inverse, it is simply a reflection over the line y equals x. So, can we say that f of x equals x squared plus 3? Can we say that that is a one-to-one function? And the answer is no, because while the original is a function, the inverse is not a function. So this is not one-to-one. Let's look at example 2. Example 2 says find the inverse of f of x equals the square root of x plus 2. They want us to graph both functions and then give the domain and range of both functions. So remember, we don't deal with f of x, so we change that to a y. And now I am ready to start the inverse. So the first step is to switch the x and y. So I get x equals the square root of y plus 2. Now I have to go through the steps of resolving for y. So the square root is isolated, so I'm going to square both sides, and that becomes x squared equals y plus 2. I now subtract 2, and my inverse equation is y equals x squared minus 2. So let's move on to graphing the function and its inverse. So remember, we first look at the original function. Now the original function is the square root. So we're going to start with the square root parent function. Now, to go from old x's to new x's, I'm going to subtract 2. So I'm going to subtract 2 from each of my x's. Now, there is no k value, so there is no change in the y value. All we're going to do is take the x's and subtract 2 from them. So what I have before me is the table for y equals the square root of x plus 2. Now remember, when forming the inverse, all you do is you flip-flop the table of the original. So you switch x and y in the table of the original, and you get the table for x squared minus 2. So here's the deal. Because we're starting with a square root has a restricted domain. So since we're starting with a restricted domain, our inverse will also have a restricted domain. That's why we don't want you trying to graph the actual x squared minus 2, because our example is a square root. We're starting with a restricted domain, so our inverse will have that same restricted domain. All right, let's look at the graph of these two functions. The original function is in blue, and the inverse is in black. Let's talk about the domain and range of the original. The domain of the original is -2 to infinity. The range of the original is 0 to infinity. Is the original a function? Yeah, it is. Let's talk about the inverse now. The domain of the inverse is 0 to infinity. And we look, and that matches the range of the original. The range of the inverse is -2 to infinity. And if we look, that matches the domain of the original. Now, is the inverse a function? Yeah, it is. So let's answer this question. Is f of x equals the square root of x plus 2 a one-to-one function? And the answer is yes, because both the original and its inverse are functions. So let's kind of sum up what we've kind of looked at in regards to example 1 and example 2. When we're just forming the straight inverse, if we start with an original function that is a parabola, our inverse will be a parabola that opens to the side because, again, it's a reflection over y equals x. If we start with a square root as the original function, then our inverse is going to be half of a parabola. So let me say that again. If we start with a square root function, our inverse is only going to be half of a parabola because of the restricted domain. So keep that in mind when you're forming your inverses. That's why we say just flip-flop the table to graph the inverse. Let's look at example 3. Example 3 wants us to find the inverse of f of x equals -2 times the square root of x plus 3. They want us to graph both functions, give the domain and range of both functions. So remember, we first got to start off. We change that f of x to y. Now, to find the inverse, we switch x and y, and then we resolve for y. Now, at this point, it doesn't matter if you divide by the -2 and then square, or if you square first. It really doesn't matter. Since you've got variables on both sides, it's 1/2 dozen the other. It doesn't matter. So I'm going to square both sides. That gets me x squared equals, now when you square a coefficient times a square root, you're going to square the coefficient and then you're going to square the square root. So -2 squared is +4, and the square root of y plus 3 is y plus 3. So again, here you can distribute or you can divide. It does not matter. I'm going to distribute, so I get 4y plus 12. You subtract 12, then you divide by 4. So there is the equation of my inverse. All right, now let's talk about graphing. We look at our original function. And since our original function is a square root, that's the function we're going to start with. So there's my square root parent function. To go from old x's to new x's, I'm going to subtract 3. And then to go from old y's to new y's, I'm going to multiply by -2. Now that I've got the table for my original function, to form the inverse, I'm simply going to switch the x's and the y's. Okay? Now remember, we started with a restricted domain, so my inverse is also going to have a restricted domain. Okay, so remember, we're starting with a square root, so our inverse will only be half of a parabola. Okay, let's look at the graph of these two. So again, the original is in blue, the inverse is in black, and it looks like they overlap in a lot more places than they actually do, but in truth, they only intersect right there. But I've put the line y equals x in there for you to see that they are indeed reflections over the line y equals x. Let's talk about the domain. The domain of the original is -3 to infinity. And the range of the original is -infinity to 0 because it's strictly decreasing. So that's why we start with -infinity. So it's -infinity to 0. Is it a function? Yes. Passes the vertical line test. Let's look at the inverse. So the inverse, the domain of the inverse is negative infinity to 0 because it's going up and to the left. So it's negative infinity to 0, and this indeed does match the range of the original. Let's talk about the range of the inverse. The range of the inverse is negative 3 to infinity. And that matches the domain of the original, but it also makes sense when looking at the graph. Is it a function? Yeah. So can we say that f of x equals negative 2 times the square root of x plus 3 is a one-to-one function? Yes, we can, because both are functions. All right, let's look at example 4. They want us to find the inverse of f of x equals 1/2 times the square root of x plus 5 minus 3. Well, remember, we don't leave things in terms of f of x. We change it to y. So that becomes y equals 1/2 times the square root of x plus 5 minus 3. So the first thing I do is I'm going to switch x and y. So that becomes x equals 1/2 times the square root of y plus 5 minus 3. So now we're ready to start solving for y. So I'm going to add 3 to both sides. That's going to give me x plus 3 equals 1/2 times the square root of y plus 5. Now, to get rid of the multiplication by 1/2, I'm going to multiply both sides by 2. So that gives me 2 times x plus 3 equals the square root of y plus 5. Now, since I've got the square root isolated, I'm going to square both sides. Now, you may ask, well, can I multiply through by 2 and change that to 2x plus 6 and then square it? The answer is yes. It really doesn't matter. But I'm just going to square both sides and then go from there. So I squared both sides. So remember, that's going to be 2 squared times x plus 3 squared. So that's going to be 4 times x plus 3 squared. Now, you're probably thinking, well, do I need to multiply that out? What form do I leave it in? Here's my thing. If they don't tell me what form to leave it in, like they don't say change it to standard form, this is already setting up nicely to be vertex form, so why make extra work on ourselves? If it doesn't specify, leave it in vertex form. So to do that, I'm just simply going to subtract 5 from both sides, and that gets me 4 times x plus 3 squared minus 5. And that's vertex form. You can just leave it. If they did want you to change it to standard form, though, that's what standard form would be. Remember, to change to standard form, you do x plus 3 times x plus 3, figure out what that is, distribute your 4, and then subtract the 5. But that's vertex form and standard form. But again, if they don't tell you, you can stop at vertex form. All right, let's look at example 5. Example 5 wants us to find the inverse of y equals 3x squared minus 4. Now, this time we're starting with a quadratic. So, the first step is to switch x and y. So I switch x and y. Now I've just got to resolve for y. So I'm going to add 4 to both sides. And I get x plus 4 equals 3y squared. So now I'm going to divide by 3. And that gets me y squared equals x plus 4 divided by 3. I'm now going to take the square root. Now, because I put the square root there, don't forget we've got to put it as plus or minus. So that gets me plus or minus the square root of x plus 4 divided by the square root of 3. Now, if you remember back, we can't leave that square root of 3 in the bottom. So we are going to multiply top and bottom by the square root of 3 because we cannot leave a square root in the denominator. Because remember, also, square root of 3 over square root of 3 is just a fancy form of 1. So again, we're not changing who the fraction is. We're just changing what it looks like. So when I multiply two radicals, I just multiply their insides together. And so that gets me plus or minus the square root of 3x plus 12 over the square root of 9. But wait, the square root of 9 is 3. So final answer is y equals plus or minus the square root of 3x plus 12 all over 3. Now, you can also change it to be the form that is up there now, because dividing by 3 is really multiplying something by 1/3. So you can kind of clean it up a little and change it to y equals plus or minus 1/3 times the square root of 3x plus 12. Now we're going to talk about function operations that involve radicals. So here's the thing. You can only add square roots if the radicand, which is the part underneath the radical, is the same. So I could add a square root of x and a square root of x, but I couldn't add a square root of x times the square root of 3x because x and 3x are not the same. So I want you to try these, pause the video, try these, and then hit play when you're ready to see your solutions and see if you did everything it asked. Okay, let's look at example A. G of x plus h of x. So I take the function g of x and add it to h of x. Well, I see that I have 3 square roots of x and 4 square roots of x. Since they are both square roots of x, I can add the numbers in front. So I get 3 plus 4 is 7, so that gets me 7 square roots of x minus 1. Now, g of x minus h of x. Now you'll notice when I'm subtracting, I put parentheses around each of my functions, so that way I do not make a sign mistake. So that becomes plus a negative 4 square roots of x. So they're both square roots of x. So I can combine them. So 3 minus 4 is negative 1. So it's negative square roots of x minus 1. Now, p of h of x. That means I'm going to take h of x, and wherever there's an x in p, I'm going to sub in 4 square roots of x. So that becomes 4 square roots of x squared. Now remember, you square the 4 and the square root. So 4 squared is 16. The square root of x is squared is x. Now we're going to do example D, h of p of 2. So the first thing I did was I found out, well, what is p of 2? Well, p of x is x squared, so that would be 2 squared, which is 4. I then took the 4 and I substituted that back into the h. So that became 4 square roots of 4. The square root of 4 is 2, so 2 times 4 is 8. So h of p of 2 is 8. For E, it wants g of p of x. That means wherever there is an x in g of x, I'm going to substitute that to be an x squared. So that becomes 3 times the square root of not x, but x squared minus 1. Well, the square root of x squared is x, so that becomes 3x minus 1. All right, last example. They want us to determine if f of x and g of x are inverses. So f of x is equal to x squared plus 3, and g of x is equal to the square root of x minus 3. Now to determine if they're inverses, listen closely. We do not want to see you take f of x, switch x and y, and resolve for y. And go, oh look, they're the same. No, we don't want you to do that. The only way to test if two functions are inverses is to do the composition of function tests. So you need to see is f of g of x, is that equal to x? And is g of f of x equal to x? Okay, so you take one, plug it into one, and then you take that and plug it back into the other. So you've got to see if when you do f of g of x, if it equals x, and if g of f of x equals x. Now, the other thing we want to tell you, do not try to do multiple cancellations per step. We will only accept one cancellation per step. Let me show you what we mean. So the first thing we're going to do is f of g of x. That means anywhere I see an x in f of x, I'm going to replace it with x minus 3, the square root of x minus 3. So that gives me, instead of x squared plus 3, it's going to give me the square root of x minus 3 squared plus 3. Well, when you square the square root, you're left with x minus 3 plus that additional 3. Well, minus 3 plus 3 equals 0, cancels out, and I'm left with x. Perfect. Now, these are the exact steps I want to see. Do not try to shortchange the process. Now let's check and see if g of f of x is also equal to x. So g of f of x, so that means anywhere I see an x in g of x, I'm going to replace it with x squared plus 3. So we have the square root of not x, but x squared plus 3 minus 3. Well, 3 minus 3 goes away, and I'm left with the square root of x squared. The square root of x squared is x. So I see that they both equal x. The composition of both functions equals x. So since they do, that means that they are inverses. And these are the exact steps we expect to see when you test if they are inverses. All right, that's it for this lesson. Your homework is worksheet 5A.3. Please remember to go out and make good choices. Please wash your hands, wear a mask, socially distance, and stay 6 feet apart. All right, until we talk again for next lesson, have a great one, and we'll talk to you soon. Bye-bye.